Right now, more than 20 billion kilometers from Earth, a machine launched before most of us were born is still sending signals home. It has been traveling through space for nearly 5 decades. Its power supply is slowly fading. Its instruments have been switched off one by one to preserve whatever energy remains. And every year, the signal becomes harder to maintain. But before this spacecraft finally falls silent, it is still doing something extraordinary. It is measuring the environment between the stars. And some of the data returned from that distant frontier can actually be converted into something human ears can hear. Not a message. Not an alien transmission. Not a voice hiding inside the darkness. Something much stranger. It is the electrical signature of plasma surrounding a spacecraft that has traveled farther from Earth than almost anything humanity has ever built. And understanding what that sound really represents makes the final years of Voyager 2 even more remarkable. Voyager 2 began its journey on August 20, 1977, just weeks before its twin spacecraft, Voyager 1. The original mission wasn't supposed to last this long. The spacecraft was designed primarily to explore the outer planets, gather scientific measurements, photograph worlds that had never been examined up close, and then continue outward into the darkness. Nobody could confidently predict that the same machine would still be communicating with Earth almost half a century later. The mission became possible because the outer planets happened to be arranged in a rare configuration. Their positions allowed Voyager 2 to use gravitational assists, essentially stealing a tiny amount of orbital energy from each giant planet and using it to accelerate toward the next destination. This technique dramatically reduced the amount of fuel the spacecraft needed. It was an opportunity so rare that another similar alignment would not occur for many decades. Voyager 2 reached Jupiter in 1979. Then came Saturn. But NASA didn't stop there. Instead of ending the mission after Saturn, engineers and scientists found a way to redirect Voyager 2 toward Uranus and eventually Neptune. That decision transformed the spacecraft from a planetary mission into one of the greatest exploration journeys in human history. In 1986, Voyager 2 became the first and still only spacecraft to visit Uranus up close. It discovered previously unknown details about the planet's atmosphere, rings, magnetic environment, and moons. Then, in 1989, it reached Neptune. There, it observed enormous atmospheric storms, examined the planet's rings, and revealed a world that looked nothing like the simple blue sphere astronomers had imagined from Earth. The Neptune encounter also marked the end of Voyager 2's planetary tour. Its cameras were no longer needed. The spacecraft was turned away from the planets and toward something much more mysterious. The space beyond the Sun's protective influence. But Voyager 2 carried something else with it. Something that wasn't designed to collect scientific measurements at all. Attached to the spacecraft was a golden record. The record contained sounds, music, greetings in different human languages, natural sounds from Earth, and carefully selected images representing our planet and its inhabitants. It was created as a kind of cosmic time capsule. A message from one civilization to whatever might someday encounter the spacecraft. The chances of another civilization ever finding it are extraordinarily small. But the message is still traveling. And so is Voyager 2. To understand where it is now, we need to understand the enormous bubble surrounding our solar system. The Sun continuously releases a stream of charged particles known as the solar wind. Those particles race outward in every direction, creating a vast region called the Heliosphere. Every planet in our solar system exists inside this enormous bubble. But the heliosphere doesn't extend forever. Eventually, the pressure of the solar wind becomes too weak to dominate the surrounding interstellar environment. At that frontier, the spacecraft enters a completely different cosmic neighborhood. The plasma becomes different. The magnetic environment changes. Energetic particles from outside the solar system become much more noticeable. For decades, scientists weren't sure exactly how sharply this transition occurred. Then Voyager 1 approached the boundary. In 2012, it crossed into what scientists now identify as interstellar space. The measurements changed dramatically. The solar wind environment weakened. Cosmic rays increased. And the spacecraft was suddenly sampling material that had originated outside the Sun's immediate domain. But one spacecraft wasn't enough to answer every question. Voyager 1 had traveled through one particular region of space. Scientists needed another measurement from another direction. That's where Voyager 2 became essential. On November 5, 2018, Voyager 2 crossed the heliopause and entered interstellar space. It was more than 40 years after launch. And its instruments detected many of the same broad changes Voyager 1 had observed years earlier. That was extremely important. It suggested that the boundary wasn't simply a strange feature encountered by one spacecraft. There really was a physical transition surrounding our solar system. A frontier where the influence of the Sun gives way to the surrounding interstellar environment. And Voyager 2 was carrying an instrument capable of measuring something particularly fascinating. The plasma wave science instrument doesn't record sound in the ordinary sense. There is no atmosphere around Voyager 2. There is no air carrying pressure waves from one place to another. So nothing like the sound of an explosion or a voice could travel through the vacuum of space. Instead, the instrument measures electrical fluctuations and plasma waves around the spacecraft. Plasma is essentially ionized matter, containing charged particles that can respond to electric and magnetic fields. Those fluctuations can occur at frequencies that, after being translated into an appropriate audio range, can be represented as sound. That's how scientists can create the eerie recordings sometimes described as the sounds of interstellar space. The spacecraft isn't literally hearing a sound. It's measuring a physical phenomenon and converting the measurement into something our ears can understand. And that distinction makes the recording more interesting, not less. Because the sound is based on an actual measurement. When Voyager crossed the heliopause, its instruments detected significant changes in the surrounding plasma. The environment outside the heliosphere was denser than the solar wind region inside it. The difference was enormous. And because plasma density affects the frequency of certain plasma oscillations, those measurements can be transformed into tones. The result is an eerie, almost otherworldly sound. But there is no hidden message inside it. No encoded warning. No artificial signal. What you're hearing is a representation of the physical environment surrounding a spacecraft millions of kilometers beyond the planets. In a strange way, Voyager is allowing us to hear something that humans could never experience directly. The space between stars. And the story becomes even more remarkable when you consider how the data reaches Earth. Voyager 2 isn't sending photographs anymore. Its surviving instruments produce streams of scientific measurements that are transmitted through an incredibly weak radio signal. By the time that signal reaches Earth, it has traveled across an enormous distance and weakened dramatically. NASA relies on the Deep Space Network to capture it. Huge radio antennas located around the world continuously track distant spacecraft. Their locations allow Earth to rotate without completely losing contact with a mission. The signal arriving from Voyager 2 is extraordinarily faint. Engineers have to isolate it from background noise, decode the telemetry, and reconstruct the scientific measurements transmitted from a spacecraft that was designed in the 1970s. Every successful transmission is therefore a remarkable engineering achievement. But the biggest problem facing Voyager 2 isn't distance. It's power. The spacecraft uses radioisotope thermoelectric generators. They don't work like solar panels. Instead, they produce electricity from the heat generated by radioactive decay. The system has been incredibly reliable. But radioactive decay cannot be stopped. As the plutonium gradually loses its ability to generate heat, the spacecraft's available electrical power decreases. That means the engineers have had to make difficult decisions. Systems that are no longer essential have been turned off. Heaters have been reduced or shut down.